Hello everyone, welcome. This is Shyam. I'm talking on behalf of Astronomy Association of Kerala, AASTRO. So we are a network of astro popularization individuals, including scientists, teachers, students. Uh, so we are kind of a mix of professionals and amateurs. So this is the September edition of our public science talk. We have been doing this for last 10 years. So we have had a wide spectra of topics, speakers, throughout these years. Today we have a very distinguished speaker from USA. So I was thinking in the morning, like today is September 11th. So like it's kind of remembered another way 20 years ago. So today we have Dr. Lap Saha. So he's currently working at Fred Lawrence Observatory, which is under Harvard Smithsonian Center for Astrophysics in Arizona, USA. He's basically from India. He did his PhD from Saha Institute of Physics in Kolkata, and he did his postdoc from I think Copernicus Center, Poland, and then from Madrid, Spain, and now he's working at Harvard Center. So his research areas are mostly high energy physics, gamma ray physics, pulsar physics, and all. Uh, I thank my friend Dr. Ashim Shegar, an astrophysicist. He actually helped me connecting with Dr. Lab. So a warm welcome for you. We have we have had a tremendous registration process. Like we have had like 150 plus registrations this time. So people from like I think all over India from different institutes. I think few of from the Middle East. Some are listening from Europe as well. I can see on the list. This talk will be streamed on YouTube and our social media handles as well. Um, I think I'll now invite Dr. Lav Saha to deliver the lecture. Thank you.
Okay, just briefly to show you all about me that, okay, you can see me. So I just switch on my video. Okay, first I like to thank Sham for organizing this. He did a lot of things on for arranging this talk. And also I'm very pleased to see a lot of people are interested in science and astronomy. So yeah, thank you all for joining. And so let me start my presentation. So you can see me, see the slides, right?
Yes, yes.
Okay,
Yes,
good.
sir.
Yeah, good. So today I'm going to tell you a wonderful field of research, which is by high energy radiation, high energy cosmic particles that we see coming from space. This tells us something deep about the properties of our cosmos, as well as some frontier aspects of particle physics, astrophysics. So that is, we are trying to explore the universe in its most extreme and violent forms. So now how we are doing this? So our nature is incredibly able to produce very high energy cosmic particles, greater than 100 tera electron volt per particle, and which exceeds by vast amount what we could see or what we could do here on Earth by man-made accelerators. You can see the difference in energy range. So in fact, you can see these cosmic accelerators everywhere. As long as you point your telescope long enough and deep enough, you can see these cosmic accelerators with their beam pointed towards us. So now the question is, general question is, how these objects are creating these particles, how they are so efficient, and how these particles from space reach these incredible energies. So we are trying to understand this as answers are using our telescopes. So before moving to that, just let me give you that brief introduction, because many of our may not be familiar with many of the things, hence I'll be discussing. So we have four cosmic messengers to understand our universe, right? We have photons, we have cosmic rays, we have neutrinos, we have gravitational waves. Now they all have their strength as well as weaknesses. For example, for photon, they are neutral, but they can get easily absorbed while traveling to Earth. Cosmic rays, we have enormous amount, but they get deflected by interstellar or intergalactic magnetic fields. We have neutrinos, they are not social particle, so they don't and interact, so it's hard to detect. Gravitational waves, they're also very hard to detect. But my talk will be mostly focused on photons. That is what I'll be talking about, not other messengers. Now, coming to this picture, this is, I think, a wonderful picture, and it tells us a lot of things. I don't know whether you have heard it, you have seen it earlier, but it tells a lot of things. For example, when you look into this picture in this radio window, you see that there is a gap, right? And again, you see some gap in the visible light. So that means in this energy range or wavelength range of the electromagnetic spectrum, they can come to Earth without getting absorbed. So somehow my cursor is not working. I don't know why. Yeah, I don't see any cursor. Anyway, I think you can follow. So now if you look into that other wave band, like some of the microwave, infrared, and infrared, X-ray and gamma ray, so you see our atmosphere is opaque to these wavelengths. So that means that, okay, you cannot detect this is photons coming from the universe being on ground. So you have to go to the above the sky to detect those photons. Now you can imagine that what will happen that if the atmosphere is not protecting us from X-rays and gamma rays, and they are not getting absorbed. So it will be catastrophic. You can understand, right? So that's why this is very important picture. You can understand a lot of things, that which of the wavelengths which are getting absorbed in the atmosphere, which are passing through it, that is transparent. So gamma rays are not transparent to atmosphere, so they get absorbed or they get they interact with atmosphere. So now we'll see. So my focus will be mostly on MeV to TeV. The MeV means mega electron volt, TeV means tera electron volt. So mostly at high energy. That's why it's quite powerful, quite energetic procedure. That's why we call it high energy astrophysics. Even an X-ray is also included in that. But when it comes to gamma ray, then we may call it very high energy gamma ray astronomy. So we do astronomy with these gamma rays, like X-ray, ultraviolet, infrared astronomy. We have gamma ray astronomy as well. So now, from the very early days, we have seen that whenever we go to a new wave band, we get a new insight about our universe, our new physics, and new astrophysics. So let me take you to a very special place in our galaxy, that is our galactic center. Now, if you look into our galactic center with the optical telescope, you will see some light, okay, blazing light, okay, that's fine. Now, but if you have infrared camera, infrared telescope, then you can actually find out that there are many stars which are transiting around a massive object, and you can in fact individually track each of that star, and from the transit of the star you can find out that there is a center with mass about 4 million solar masses. So okay, apart from infrared, we see, okay, apart from this star transit, we don't see any other activities. So it's quite dormant in that galactic center. But now you try to look in this region with our GVTV telescope or gamma rays, you'll see a blazing source. You can see on the left, that picture, lower left. So it goes, you see the Milky Way, and above that you see, and below you see a blazing object. That is basically gamma ray emission coming from that region. So even if you go to even higher energy, tera-electron volt gamma rays, that is 10 to the 12 electron volt, you see also bright spot. So if you look into just go to that infrared or optical, you don't see any that kind of object is present there. So this is quite fascinating that whenever you go to a new wave band, you'll see something different, you'll discover something different, you get new insight. So with this brief introduction, let me just give you an outline what I'm going to next. I'll be talking about gamma ray astronomy, some of the first detectors we had, then what is the main scientific motivation. Then I'll give you a present landscape, that is what detection techniques we are using now, what are the recent scientific highlights, that is very important, of course, from the science aspects, and then future, what we are going to do in future, what are the new instruments coming up. So now the first question we can ask, how do cosmic accelerators produce such extreme energies? And the answer is Fermi shock acceleration mechanism. It's a theoretical procedure through which we try to explain these very high energy particles, how they are getting accelerated. So what is happening in a very simple way, when a shock is getting generated by supernova explosion like that, so that shock moves in the interstellar medium, and that traps particles that are bounced back and forth across the shock over many years, and they can and boost these particles to very high energies like TeV, tera-electron volt, giga-electron volt, even high energies. So this is the general concept for this acceleration. Now the question is, okay, we want to track down all these cosmic accelerators, right? So we need to detect cosmic particles. Cosmic particles mostly consist, 99% of them are basically protons, and a few others are heavy nuclei or electron. So whenever we talk about cosmic particles, we are talking mostly about protons. Okay, now the question is, then we can detect these protons to detect these cosmic accelerators or origin of these cosmic particles. But then why I'm talking about gamma rays or photons specifically? The reason that you know that cosmic particles are charged, so they will lose their directional information while traveling to Earth by the interstellar intergalactic magnetic field. So when you will have that particle, you won't be able to make out from where it came. But if you have a neutral radiation like gamma rays, then you can easily pinpoint those cosmic accelerators or original. So now next question, how these gamma rays are being produced. So we have standard physical procedure, probably you have heard in your physics classes: synchrotron emission, curvature radiation, inverse Compton, Bremsstrahlung process. They are essentially associated with leptons, means electrons. And when it comes to protons, protons can interact with through different channel like proton antiproton annihilation. They can produce pi zeros, neutral pions, and these neutral pions can decay into gamma rays, and in that way they can produce gamma rays through hadronic procedure. So we generally categorize them into two parts, leptonic and hadronic. So we have some mechanism to produce gamma rays from these very high energy particles. So now, how gamma ray astronomy was started. So it was essentially a serendipitous discovery. How? So in 1967, and there are some US satellite that was meant to detect gamma ray radiation emitted from nuclear weapon tests. You know that if you go for a nuclear weapon test, then you will see they will emit gamma rays. So idea was to get observed gamma rays from the Earth, not from the space. But yeah, it happened that they didn't find anything coming from the Earth. Rather, something was coming from the space. So that led to the discovery, start of our gamma ray astronomy. So in 1967, we had the idea that, okay, we can do gamma ray astronomy, or astronomy with gamma rays, but it took another 22 years to bear fruit. And we just discovered the gamma rays from Crab Nebula, which was already known by then that it was emitting in optical, X-ray, infrared, and all wavebands, but not in gamma ray. So by that time, 1989, when we had our gamma ray telescope ready, we built 10-meter telescope, which was located at the place where I'm working now. So we found TVA gamma rays from this Crab Nebula, and that was detected using this telescope. Then later, 2 years later, we sent another telescope and that is satellite based, that is Compton and Gamma Ray Observatory, and that also gave us a lot of information about gamma ray sky. So now with this, just let me tell you the brief scientific motivation then and on about gamma ray astronomy, that we are of course doing extreme astrophysics to understand the origin of high energy particles. Then we would like to understand what are the emission mechanism is going on within the source. We can also test for low range invariance violation. We can try to get estimate of the extragalactic background light at which through VHE emission, very high energy gamma ray emission from active galactic nuclei, and then multi-messenger astronomy. So once we have information about cosmic rays, gamma rays, neutrinos, gravitational waves, they can give us complementary views about the source. And we can do some much more beyond standard model. We can search for new particles, new relics, and we can get the signature of dark matter in our universe. So now moving on to the next, that is present landscape, detection technique, exciting experiments, and recent scientific highlights. So what are the experiment techniques are being used? So I have already mentioned that atmosphere is opaque to gamma rays. So you have to go above the sky, above the atmosphere, to detect gamma rays. But of course, there is also technique to detect gamma rays being at ground, that is ground-based telescopes. And we know these gamma rays covers a wide energy range, and from 10 mega electron volt to all the way up to tera electron volt. So one single detector is not sufficient to detect gamma rays. So we need to have multiple telescopes. So yeah, our space-based telescope, they cover a particular energy range, and then if you go to ground-based, they cover a different energy range. And you can see the range mentioned in this picture. So now, one of the important currently running gamma ray telescope, space-based, that is satellite-based. This is called Fermilat. So it's essentially a particle detector at space. How the detection is being made, like a gamma ray, which enters into the atmosphere and enters into that detector, and that interacts with some conversion material, and that produce electron-positron pair. Very simple procedure. And this electron-positron pair, they move down through the particle tracking detectors, and then with calorimeter we can get the energy estimate of this electron and positron, and from the tracking through this detector we can find out from which direction these gamma rays are coming. So we can get both information like direction as well as energy. And then we have detection technique at ground. Like what is happening here when gamma ray enters into the Earth atmosphere, it interacts with the Earth atmospheric particle, and this produces electron-positron pair again. And then this electron-positron pair produce further decay or emit radiation, and then they produce a shower called electromagnetic shower. You can see in that cartoon picture. Then this electromagnetic shower is producing chain of light. You see this blue light, and this blue light is coming on the telescope and falling on the telescope mirror surface, and then from there it's getting projected to the camera, and in this camera we get the picture. Okay, so this is more or less also very simple procedure, but yeah, it's not that simple it seems. So let me show now, bring it to that how our picture will look like in the camera plane. When a chunk of light is coming, it's a kind of a flash, 10 nanosecond flash, and you see the picture here. It says the typical image will have when it will be detected by our camera. So if we have more than one telescope, like stereoscopic view, then you get the idea that the orientation of the image will be different and on the camera plane, and from that you can essentially find out the direction from which the gamma rays are coming, and also from the image phase density, or what we call, I'm just trying to explain it in simple term. So how bright is the image, what is the extension of the image, based on that you can essentially find out the energy of the gamma ray. So this is the way we do it in ground for the ground-based telescope. So now, what are the ground-based telescopes are there in the world? And so what are the Indian contribution, right? So we have 3 Indian experiments. One is still going on. I mean, it's in commissioning phase. I'm not bringing that, but earlier experiments like PACT, which was located at Pachmari, Madhya Pradesh. Tactic was at Mount Abu. Hagar is Hanle, Ladakh region. And apart from that, we have other experiments all over the world. Like we have Tibet, Argo in China, then we had Kangaroo in Australia, Haze in Namibia. This is European project. Hawk is also American project. It's in Mexico. In Veritas, Whipple, this is the place where I'm working now. And Magic, which is in La Palma, Spain. And I have had worked earlier with Magic. So you see a lot of telescope, but currently a running telescope, Magic, Veritas, and Haze. These three telescopes, and Hawk is also there, and Tibet, they are also there. But in Indian, experiments are mostly not in that active phase. So with this is a little bit about what are the experiments we have on gamma ray astronomy in the world. Let's move on to the many phases of cosmic accelerators. So we have different types of sources. You have heard about these sources like Pulsar, Galactic Supernova remnants, star cluster, Pulsar with nebulae, binary systems. They're all galactic sources in our galaxy, and they also emit gamma rays apart from lower waveband like radio, X-ray, infrared. So they also emit gamma rays. Apart from that galactic source, we have also extragalactic, that is off the galactic plane. We have active galactic nuclei, and we have starburst galaxies. They also are quite active in gamma rays. So now, trying to give you brief scientific highlights what we are doing presently and what are the interesting facts going on. So first, of course, that we are still trying to understand the origin of cosmic rays, and which was first discovered by Victor Hess in 1912, which led to this Nobel Prize in 1936. So our origin of cosmic rays still a mystery. Of course, we have solved. So that's why we have a standard paradigm. Within that, we consider the supernova origin. However, to solve the mystery, we need to understand that we need to detect TeV gamma rays from supernova remnants. We must show that supernova gamma rays are from hadrons, not from leptons like electron. And also, they must show that there are many supernova remnants. They can generate cosmic rays. That's the way we can say that which one is the origin, which class of sources uh, is responsible for these cosmic rays. Now, for example, just let me give you one example on that. This is a Taiko supernova, and we have the flux here. You can see flux means on the x-axis we have energy, and the y-axis we have number of photons per centimeter square per second per energy range. So once we have the flux, we try to find out which emission procedure is trying to feed the data very well. And if we see that hadronic emission process can explain the data very well, then we see, okay, then we get the hint or evidence that hadrons or protons are getting accelerated in that source. That's the way we try to figure out whether the source is a cosmic accelerators or not. So we have another source, Cassiopeia A. It shows similar behavior. I'm not going into much detail, but yeah, if you have any further question on that, you can ask later. Now coming to highlight 2, we have extragalactic object. They are observed in all wavebands, like for example here for a particular source, radio, optical, UV, X-ray, and gamma rays. And they are quite often, they are flaring kind of object. They flare quite often. So it's quite interesting source for us to study and try to see whether they emit photons or not, or they are accelerating particles or not. Now, highlight 3, explaining the unknown. So recently, our Fermi-led telescope, this satellite-based telescope, they have given a catalog. Means they have detected many sources with some of them are known pulsars, supernova remnants. Some of them are blazars or active galactic nuclei. But you see, about 28.2% of them are known. So you see, that's quite fascinating that we have still a lot of sources which you don't know. And some of the people are trying to think that it may be associated with dark matter. So that is another mystery in our universe. So similarly, if we go to very high energy like 200 gigaelectron volt, we see there are 36 non-firmly identified. So we get gamma rays from these sources, but we don't know what kind of sources they are, whether they are pulsars, they are supernova remnants. No, we don't have any idea about them. So now highlight 4, we are trying to also get information about some of the gamma ray binaries. They are, of course, emitting gamma rays. That's why we call gamma rays. There are a lot of X-ray binaries, but we have 10, 11 gamma ray binaries so far detected. So they have two different scenarios. One is called microquasar, another one is binary pulsar, that is the compact object, whether it's a black hole or it's the neutron star. Or that can, based on that, we have this classification. So now highlight number 5, unusual stories from pulsar. We have so far 3 pulsar detected at very high energy gamma rays, like up to, it can go up to 1.5 tera electron volt, like Crab, Vela, Geminga. And Geminga was the new addition to this class. So you see, we have just with our art of state-of-art detectors, we are just trying to find out more and more sources as in this energy range. And we are quite successful in doing that. Now highlight 6, indirect detection of dark matter. I say, if you know that WIMPs particle, that those are weakly interacting massive particle associated with dark matter particle. And they emit when they annihilate, they can produce gamma ray signals as well as neutrino. So once you know that there is a potential source which you can consider, okay, this could be a potential dark matter source, then you point your telescope towards it and you try to find out whether you see gamma ray signal or any neutrino signal with neutrino telescope. And if you get it, then probably you'll try to, you may solve the greatest mystery of the universe, that is dark matter. So we are also trying to do that kind of physics with our gamma ray telescope. And highlight 7 is my multi-messenger initiative. So once we have gamma rays, cosmic rays, we try to combine with LIGO data like gravitational wave data as well as neutrino data together. So let me give you one example with that. So you know that it was gravitational, it was already detected, but in 2017, and there was a special event. And that special event was the first event which was detected, in LIGO detector, Virgo detector, as well as all other wave bands, including optical, also in gamma rays. So that was the first time we saw that there is an association with this emission, electromagnetic parts as well as gravitational counterpart. So that kind of thing we are now this is very recent development. So with our telescope, we can do that now. So I know, we hope in future we'll have many such events. So another interesting thing in the multi-messenger aspect is neutrino follow-up. So on 22nd September 2017, IceCube detected one neutrino event. And then at the same time, almost at the same time, we detected gamma rays from a blazar. So, and we see that the emission is neutrino emission as well as gamma ray emission was coming from the same region of the sky. So that led to the discovery that this blazar is basically essentially accelerating particles, very high energy particles, and these very high energy cosmic particles are giving rise to this neutrino. So that association, in theory, it was there, but experimentally, that was the first time it was verified. So we had a science paper on that, based on that. And also recently, another thing, you have heard a lot about GRBs, but mostly GRBs. So you may think, oh, what's new about GRB? So the interesting thing is that GRB was mostly detected up to 100 gigaelectron volt. But this is first time we detected it up to 1 tera electron volt. So 1,000 times more than what 10, sorry, not 1,000, but 10 times more than what we had predicted earlier. So this we had that led to our Nature paper also. So this is also quite, so we also hope with our next generation of telescope, we'll discover many such telescopes. Many such sources. So now coming to the another interesting part, many people are interested in deep learning nowadays. As people are doing these supervised learning algorithms, decision, and this is all a part of this artificial neural network procedure. And we have images, lot of images, and we try to understand this image is a fake event or real event. So people now working on that aspects, that, oh, well, we can really, with this neural network method or artificial intelligence, we can figure out whether this event, this image corresponds to a gamma event or a different type of event. So that we are trying to do. A lot of people are involved in this thing. So it's quite interesting for young generation. Many people are involved in this computer related and mostly simulation and all this stuff. So yeah, apart from the taking part in observation, you can do this kind of work as well. So now coming to the future, what are there in future for us? So far we know that gamma astronomy comes of age. And in pre-1990, our prediction was, expectation was like that, we'll find the cosmic accelerators, probably supernova remnant. And what is the reality in 2021? We have astonishing variety of very high energy emitters. We have lot of sources within our Milky Way and above the Milky Way, extragalactic objects. So now, but we have not reached limit of the technique yet. Why? So you see, let me give you the brief idea again, that the light pool, Cherenkov light pool, what we have shown or discussed earlier, this is about 100 to 200 meter. Okay, so suppose we have 4 telescopes. So most of the cases, these showers or this Cherenkov pool miss the sweet spot, which you can see with this rectangular box. So if it is falling at the sweet spot, then all 4 telescopes can detect that. But it's rarely happens. So we don't have good resolution of images. But what if we put many such telescopes? So Cherenkov light pool can find some sweet spot for some of the telescopes. And that's the idea behind the CTA. CTA stands for Cherenkov Telescope Array. That is, we are going to build. We have built some of them, but since there, you can see from the picture, there are a lot of telescopes should be there. So we are coming up one after another. So that's why CTA Cherenkov Telescope Array we call big eyes with sharper views. So let me give you again the CTA overview. So there will be different types of telescope. We'll have 3 different types of telescope. Like, of course, their sizes are different. Like one is 23 meter diameter, which is quite huge, and then We have 9.7 meter to 12 meter diameter telescope for medium energy, and for high energy we have small size telescope that is 4 meter diameter. So 3 different types of telescope will be there, and we have already sites decided. We will have one at northern hemisphere like Spain, another one is in Chile, southern hemisphere. Now why we go for 2 different hemisphere? So from the northern hemisphere we can detect northern sky, we can cover the fully northern sky, and from the southern hemisphere we can cover the southern sky. That's the reason we have telescopes at 2 different places. So, and there are a lot of countries involved, a lot of institutes are involved, including India. Some of the Indian institutes are involved. This is so far September, based on September 2020 documentation on the CTA consortium. So in just one picture, we can explain the capabilities of CTA. So with our present generation of telescope, you can see that how much we can see. It's a small part of our galaxy. With CTA, we can cover the entire part. So you can see how the CTA is going to be. So with this, let me show a prototype large size telescope. Of course, we'll be thinking that where is the telescope? Is there already there, or it's in the paper? No, it's already on the ground. So let me just run it. You can see how it's flew. So you can see the camera at the focal plane. So this is, we are testing that how it was moving, how fast it can move, and all this stuff. So this is already there, but many such telescopes will come of that size, mostly 4 on the northern hemisphere. Then we have another telescope. Of course, this one I have worked earlier. Now I'm working on this one. This is called prototype Schwarzschild telescope. And this is also located at the Fred Lawrence Whipple Observatory, Arizona. And you can get much more information on this telescopes when you go to this link. And you see it's quite different from the previous one. And here you see mirror here and also here. So we have 2 different types of mirrors we call primary mirror, and then we have secondary mirrors. From the primary mirror, light is going to the secondary mirror, and from secondary mirror to the camera. So it's a bit different type of telescope than the previous one, and its sensitivity is also quite different. So that's all. So let me just briefly tell you the summary, that this is a very fascinating field with huge discovery potential. High-energy photons probe astrophysics of TV particle acceleration in the cosmos, and that is not yet tested or understood by any other means. And it is equally important for very high-energy photon to search for new physics beyond standard model. People are doing that. And CTA is going to be a discovery engine. So that's all about my talk. But before finally finishing this, let me show you one video that is made by our CTA for outreach purpose. You may find it interesting. So hope you can hear that.
With our eyes, we see only a tiny fraction of the light in the universe. To see more, we need instruments that can see light we can't. Like gamma rays, the result of subatomic particles accelerated in violent places like stellar explosions, or the jets discharged by supermassive black holes. Nothing generated on Earth comes close to the energy of the highest energy gamma rays. They can fly through the universe without getting scrambled by magnetic fields. We can't see them coming, but they travel directly towards us. But they never actually make it to the Earth's surface. They interact with the atmosphere, producing cascades of high-energy subatomic particles. These energetic particles move faster than the light in the air. And like a plane creates a sonic boom, they create a photonic boom. It's called Cherenkov light. It's blue, and it's spectacular. But this happens in a billionth of a second, so we need powerful telescopes to see it. Like CTA, 2 arrays of telescopes, one in the Atacama Desert in Chile, and another atop the Spanish island of La Palma. The Cherenkov light will flash and disappear. This faint glimmer can be collected by the telescope's mirrors and reflected into cameras, capturing 1 billion frames per second. The light will be captured by sensors able to detect a single photon and turn it into digital data. Data centers will store and process the information, so scientists can work with it. The telescopes are positioned to increase our chances of detecting Cherenkov light. More telescopes gives us more information. By layering these images, we can estimate the energy of the gamma ray and pinpoint its direction in the sky. The data will be accessible to anyone, anywhere, so the discoveries are limitless. Precious information carried by invisible gamma rays, allowing us to see into the most unknown parts of the universe to help unlock its secrets.
So that's all.
Thank you very much, Dr. Lab. It was kind of a very inspiring lecture, and especially that video you have shown towards the end. And now I think we'll have some questions. So the participants, either they can use their microphone, or we have a comment box. If you want to put your questions on the comment box, we can ask it. There is one question. Are Cherenkov lights always blue? That's the question.
Yes, Cherenkov lights are always blue. Yeah, it's within a range. It's not a fixed particular wavelength, but of course our blue has a spread, and so yeah, in the wavelength. So yeah, but it's blue.
Okay, Dr. Lab, I have a question about this Pulsar search techniques. Like, I'm not very sure about the term. I've heard like you use these fast folding algorithms and Fourier transform things, to get the periodicity thing. So
Yes.
I was just wondering, how do you distinguish like pulsars from other, signal emitting objects?
Okay. First of all, it is more relevant when people are going for blind search. That means you don't know that whether it's a pulsar or not. So we do go have a lot of detected sources as by Fermilab, and then they run blind search algorithm to find out any periodicity is there or not. So that's the way we do. But when we go to the ground-based telescopes, then our energy range is quite high. Then generally at the time we don't have that much statistic. As I just said, that we have only 3 detected sources. So it's not really, we don't really use that algorithm. I mean, it doesn't make sense to use that unless you have a lot of sources which are unknown. And of course, for this algorithm, you have to give the exposure. I mean, and your data should be quite sufficient for this algorithm to work. But yes, I mean, if we see that periodicity is there, then that is not even sufficient. And that, okay, if you see periodicity, then that's. But this periodicity, whether it's associated with a millisecond pulsar or it's a binary, because sometimes binary can show you, like for example, if we go for this on binary source and we see the periodicity as 26 days or 27 days, then we don't consider it's a pulsar. So that's the way we can rule out which one is pulsar, which one is binary system. So this is the way we proceed. So it's not just one algorithm which can just indirectly tell us that this is a pulsar. No, we have to do a lot of tests. And also whether we have to see that meets the criteria, like what kind of pulsation it has, what is the periodicity, and all this stuff.
I have a question from Krishna Kumar. So he was asking how we are looking forward for handling the solar modulation effects in regards CTA experiment. Do CTA have adopted any new measures and methods to deal with the solar modulation effect on signal from cosmic accelerator?
Yeah, first of all, CTA is ground-based telescope. Well, right. So ground-based telescope. So when cosmic rays are getting interacting, cosmic ray can also interact at the top of the atmosphere, and also they can mimic like a gamma ray. So your question is very nice, that whether this kind of sudden surge in cosmic rays. But ground-based detectors, whatever cosmic ray acceleration is coming from the solar modulation, that is very low. I mean, compared to what kind of detection we do at ground. So they won't be able to make out the light which is really sensitive for our camera. So that's why we don't really talk about solar modulation, because we know that through solar modulation what kind of cosmic rays we are getting, and because we are not detecting cosmic rays, we are detecting chain of light, and that light is being produced by cosmic rays. And how much light we need in our detector, this low energy cosmic particle from solar modulation, they cannot produce that much of light to trigger our system. So we really don't need to worry about this thing for our, but yeah, it's very important for satellite-based telescopes. Yeah, for satellite-based telescope, yes. Then you just if you know that, you switch off the telescope. Yeah, because they can affect in different ways. So for CTA, we don't, at least for CTA is ground-based, so we don't need to worry about this solar modulation. Okay, the second question is there any possibility of false detection of high energy particles? Yes, of course we have. How? As I said, that false detection can come from different things. One is cosmic rays. Cosmic rays means proton that interacts at the top of the atmosphere, then can also produce chunk of light, like gamma rays. But the image shape of a gamma ray and cosmic ray will look a bit different. Okay, so now we have multiple telescope, and we know that the light, chunk of light spread, and like I said, 1 billionth of a second, our flash will come. Now, in this within this time window, we can see that what kind of images we are getting. The image is very like elliptical shape. Then we consider, okay, it's more likely gamma ray. Again, we say likely. Then we verify, try to understand that what other telescopes, the same event, what appeared in other telescope. It's a similar kind of image, or it's more blurry or more spread out. So based on that, we try to understand. Again, it is all done through simulation. Okay, so this is through simulation, we try to understand whether if a real gamma ray is hitting our telescope, what the image will look like, and what if a cosmic ray, what that will look like. So we try to understand that. So it goes through some processing. Then we say, okay, it's more likely a gamma ray source, gamma ray event. And it also other way of mimicking, but that is easy to reject. Like we have lot of night sky background noise, like some noise, local light from other stars coming. They can also produce mimic like a chain of image, but it is easy to reject them based on 2 telescope combination, 3 telescope combination, and because they are not within this very narrow time window, within few nanoseconds. If it is from different object, then it won't be, it might be blue light, because of course blue light is coming from all stars and all this thing, but that we can easily reject them because they are not, we have a coincidence window. Like for example, okay, let us take 60 nanosecond. Within this 60 nanosecond, how many events are coming? So if we can see that, we can easily detect, just separate out those fake events. So that's the way we do it. So yeah, false detection is there, but at 99% and confidence, we can reject many of them. Okay, they are 2 different objects, black holes and pulsars. They have different phase. They are different objects. That's why it depends on mass and all this thing. And pulsar is mostly neutron star. You know that neutron star phase, and when it goes to black hole and all this thing, they depends on mass and all this stuff.
Hello, am I audible?
Yes, yes.
Yeah. First of all, thank you, Dr. Saha, for your very nice talk. It was very interesting and thought-provoking. And I have a question out of curiosity. Unlike other things that we are trying to detect here, like the neutrinos or something, these cosmic rays are pretty destructive in nature. So, shall we?
Sorry, your voice is just going up and down. Can you repeat the question again?
Okay, sorry, I will repeat. Unlike other things that we are trying to detect in science, these cosmic rays are actually destructive in nature. So,
yes.
Should we expect that the apparatus responsible for the detection process have a shorter lifespan compared to other telescopes and etc.?
Can you explain exactly what you mean by, because I don't understand destructive. Okay, it's a destructive in different way, yeah. You can say.
Yeah, they have high energy. No? They are. Should we need any radiation hardening or anything for these, especially if we have any equipment on space or even balloon-based equipment for the detection of these rays?
Okay. I mean, you mean that those instruments are suitable when there is, I mean, and there is a destructive nature of this particle on
Yeah.
this, an effect on these instruments, right?
Yes.
Yeah. Okay. So it's very simple in the sense. Suppose if I go for a balloon-borne experiment, like you want to detect the cosmic rays, so those are designed to detect cosmic rays, right? So those could be scintillator detector and all these things. So they don't have any effect on the detector itself, but sometimes electronics, you know that if you get a huge static charge, your electronics may fail. So that kind of destructive nature it has, of course. But again, then you have to do the grounding work very well, so that you don't destroy your instrument. So people know it very well, that how to manage all these things. Okay, so but now if you come to the ground-based telescope, so when it comes to ground level, that level, you know that, okay, there are a lot of cosmic particles are coming as well. And also it's very easy to just subtract those and effect easily by doing grounding. We also do for our telescope, like we know that it's just a problem of static charge, nothing more than that. So one particle, like one very high energy particle, I mean, that can come to the ground or surface of the earth, and that may have some effect, but number of such particle is very low. As you go to the high energy, number of particles per unit area per unit time, it goes down very rapidly. So that's why atmosphere is basically protecting us from the cosmic rays. That's why if you go to high altitude, very often you will get the shock, static charge shock. I feel it very often. I mean, you touch something, you'll get a shock. So it's all static charge problem. So because if you up above the sky, up in some mountain, you'll get that feeling. But when you're sea level, that you don't see, because it's already absorbed in the atmosphere. So that effect on our instruments at ground has little effect for the cosmic rays. But yeah, the effect is there for instruments like satellite instrument or balloon-borne experiment or whatever instrument, but we know how to handle this thing.
Yeah, thank you. Well, let me add another question, which I got inspired from your answer. Since the atmosphere is absorbing cosmic rays, and can we expect it to leave some chemical trails, which can be used as an evidence how they are interacting with us? I mean, is that actually affecting the composition of the atmosphere?
It's we have a lot of oxygen, nitrogen, and all these things. So mostly it's interacting with those molecules. But compared to the amount we have. But of course, how do I know that how cosmic rays is information? I mean, we know that it produces a shower of cosmic ray produce shower of different particles. Okay, we know it. How do we know? Because we can basically track them down. If you put your balloon at different height, in your detector you measure all these particles cosmic rays are producing, all different elements. Okay, even different and chemical composition means when you see chemical I consider it basically you meant different particle shower. Its atmosphere is basically breaking, oxygen and molecule is breaking, nitrogen molecule they are breaking, but when it's a cosmic ray coming, there's a proton, okay, or little bit of heavy nuclei, they can break, of course, into lower mass particle. But yes, we can track them, our scintillator detector, which one is what. We can also detect muon. You know, that's our particle detectors are also there at ground. We can detect muon, and all sort of particle we can detect. Neutrino, we can detect atmospheric neutrino. You know that neutrinos, when I was talking about neutrino, I was not talking about atmospheric neutrino. We are talking about astrophysical neutrino. You get all neutrinos all the time in the atmosphere. That is why how it is coming. It is all because of these cosmic particles. So we can understand which one is what kind of particles are coming. We can track them with scintillator detectors. Yeah, we have some detectors at Graves UT. That is called Graves particle detectors. In that detector, we detect those particles.
Okay, thank you.
There are 3 questions on the comment box.
I said, do cosmic ray influence lighting in atmosphere? I'm not really sure about this fully because I heard about this. Some people try to say that if it produces a lot of charge, then it may influence lightning. But yeah, then it may happen that suddenly you see lightning without any cloud in the sky, but we don't see really. I mean, just trying to guess that we don't really see any lightning if the sky is clear. So if cosmic rays are responsible, then there should not be cloud, and we see there. I mean, some very often this lightning. So I'm not sure though, but yeah, lightning, maybe it's causing, but those are not reachable to the ground, so we don't really feel that. But of course, they are producing showers, little bit of electrostatic effect could be there. But what we mean by lightning, what we generally understand, probably that is not happening due to cosmic rays. So this is, we can just infer from our observation. And then another question, are there any other natural bodies in the universe that can emit stable signal like pulsar? Natural bodies like pulse. Okay, pulsars, you are saying pulsar stable because all the time you see it's repetitive, right? Repetitive means, okay, they are all crab nebula. This is always emitting. So I don't know whether you want to understand that, or you mean something. Stable signals mean Sham, I don't know what exactly you mean by stable signals. And stable means, yeah.
Someone sent me this question. Yeah. Okay, I have another question. It's about the frequency. It's like we have these high frequency pulsars and low frequency pulsars. So roughly, how many pulses per second, minute, or what's the magnitude of that? Like,
Okay, so it's mostly when we call millisecond pulsar, that is pulsating in millisecond, like crab pulsar, that is 33 millisecond. Okay, so in each 33 millisecond, you get a pulse. Okay, now we have a normal pulsar. That is pulsation in seconds order. So it's millisecond to second order.
so do we have pulsars with very long period?
As far as I know, if we see, like, for example, then we call probably that is associated mostly with some pulsar 3.43 millisecond, 10 second, 3 second or something, 4 second. exactly, of course, it depends exactly, but it's roughly order in that magnitude. But if you say 1 day, no, I don't know any pulsar with it 1 day a pulsation period that we call some binaries. Okay, binaries show that kind of behavior. Binary, that means another object is there.
Okay, we have a school student, Arjun. Arjun, you want to ask a question?
Yes, sir. My question is, are there are there pulsars which pulsate so fast that when we observe it, it looks like it is not pulsating?
Yes, if it is doing that, then it means that we don't have the capability of detecting the uh, detecting its pulsation, because we have limitation on our detectors. But nevertheless, there could be many reasons for not detecting the pulsation. Like one, okay, it's pulsating so fast, or maybe it is not pointed directly towards us. If it is not direct, its beam is not towards us, then probably we won't make out whether it's pulsating or not. So there are many pulsars are there, but it's not pointing towards us. Its beam is not pointing, so we won't be able to make out whether it's pulsating or not. But again, if it is frequencies too much, but there, of course, there is a theoretical limit up to which I'm not sure exactly up to which it can pulse based on mass and all these things. So yeah, that is possible, but we don't really think that mostly we consider that, okay, even if it is pulsar, but it's just because probably it's not pointed directly towards us. But your question is quite valid, that if it is there, if theoretical limits permit that, then that could be a reason, if our detectors are not that sensitive.
Okay, sir. I have also one more doubt. So, as you had said earlier, there is a theoretical limit to like the what how fast like pulses we can actually detect with our equipment currently. So, like what is the limit like currently? How
Okay,
many
so
pulses per
yeah,
second?
I'm sorry, because I'm not a pulsar expert, so I'm not doing also theoretically on pulsar, so maybe I'm not totally sure, or if exactly what could be the limit at, and yeah, I'm sorry for that, not answering your question.
Okay, sir. Thank you.
There's one more question. Still again, pulsars, are they radioactive?
If they are radioactive, I think I don't know whether radioactive means whether they have radioactive materials, right? So yeah, I don't think.
But love the, when
Yeah,
when
I'm
you look
not
at
really.
this gamma ray, sorry,
Yeah.
when you look at these gamma ray spectra, like there are some kind of spontaneous, peaks and valleys kind of thing. So can it be, kind of a consequence of a nuclear, a fission kind of thing or something?
Okay. Now see. Okay, I can say that radioactive. What we mean by radioactive, when we have radioactive material, they emit maximum in the MEV range, very little of MEV range. Okay. So but when we talk about gamma rays, that gamma rays are not in they are far beyond these radioactive gamma rays, what we use lab for cancer treatment and whatever. The energy of this gamma ray we are detecting are much higher than what radioactive material can emit. So if you think, okay, the pulsars, they are, I see gamma rays, so whether they are radioactive, of course no. Then answer will be no, because those gamma rays we are getting not because of radioactive material there. It's on because of a non-thermal procedure in which high energy particles are producing this energy. So not from from the decay of radioactive material. That won't reach us. That won't reach us.
Okay, thank you. Anybody else? Any questions? If not, I think we can conclude.
Okay, thank you. Thank you very much all for your question and joining this.
Thank you very much, Dr. La, for spending your valuable time. It's like 5 o'clock in the morning. So yeah, so we are looking forward to have more collaboration with you. If you are, when you are coming to India, we are happy to host you in Trivandrum. So please let us know.
Okay, sure.
Thanks everybody. Thank you so much for joining the talk. Thank you, Dr. Lal. Thank you.
Okay. Thank you. Bye.